Picture this. You are a paleontologist in the Patagonian Badlands of Argentina, sometime in the late 1990s. The landscape around you is the specific kind of beautiful that only exists in places where the wind has been working on the rock for millions of years. Eroded columns, exposed strata in bands of rust and ochre and gray, the occasional fossil fragment sticking out of a hillside like the earth is trying to show you something. You have been out here for weeks. You have found some interesting material, but nothing extraordinary. Your knees hurt. Your field assistant is significantly less enthusiastic than they were in week one. And then you see something sticking out of a cliff face that stops you mid-step. A bone. A very large bone. Larger than you expected. Larger as you get closer than seems entirely reasonable for any animal you have a clear mental model of. You start excavating. More bone. More. A femur emerges, that is, when you stand it upright, taller than you are. The implications of what a femur this size suggests about the animal that walked on it begin organizing themselves into a sequence of calculations that your brain is running slightly ahead of your ability to process them. You are looking at the remains of Patagodaton majorum, or something very much like it. And what you are about to spend the next several years extracting from this hillside is the skeleton of an animal so large that when it is eventually mounted in the American Museum of Natural History, its neck extends through a doorway into a neighboring corridor because the main gallery is not long enough to contain it. The skeleton is over 37 meters long. The animal it belonged to weighed an estimated 70 tons. It is the largest land animal for which we have skeletal evidence, and looking at its femur while standing next to it produces a specific quality of cognitive vertigo that photos of it do not fully convey. This is what animal skeletons can do. They produce encounters with scales of life, forms of existence, and biological engineering solutions that the living world around us does not prepare you for. The fossil record, and the full range of existing animal skeletal diversity, contain structures so strange, so extreme, so seemingly improbable that examining them carefully changes how you think about what a body can be and what evolution can produce when it runs without constraints for long enough. So here is the full tour. The strangest, most extreme, most architecturally baffling animal skeletons ever found, with the honest explanation of what each one is doing and why it exists in the form it does. Start with the Babirusa, because the Babirusa is alive right now, walking around in the forests of Sulawesi, Indonesia, and its skull is strange enough to belong in any discussion of skeletal extremity, even without the additional drama of geological age. The Babirusa is a pig, a member of the family Suidae, broadly related to domestic pigs and wild boars. But its skull has done something that no other pig's skull has done, and that looks, when you see it in skeletal form, like the product of a fever dream rather than natural selection. The male Babirusa has 4 tusks. 2 of them emerge from the lower jaw in the standard pig configuration. The other 2 emerge from the upper jaw and then do something that upper jaw tusks in almost every other tusked animal do not do. They grow upward, curving back toward and sometimes into the skull itself, piercing through the skin of the snout and continuing to grow in a long, curving arc toward the skull cap. In old males, the upper tusks can complete enough of their arc to actually make contact with the skull, at which point, in the absence of dental wear or breakage, they would eventually penetrate the skull from outside. The skeletal structure of a Babirusa skull, with the lower tusks pointing forward and down and the upper tusks growing upward through the snout in curving arcs toward the animal's own head, looks like something a special effects department produced for a fantasy film rather than something that occurred through the normal processes of biological evolution. The functional explanation that the upper tusks may function as a guard or parrying structure during male-male combat, deflecting blows from other males' lower tusks away from the face, is plausible and has supporting evidence, but it does not fully dispel the impression that natural selection was, in this specific case, making things up as it went. Move to Dunkleosteus, the armored fish of the Devonian period. Because Dunkleosteus is where the skeletal record starts producing things that the living ocean does not prepare you for. Dunkleosteus was a placoderm, an armored fish that lived approximately 350 to 380 million years ago. And its preserved remains consist primarily of the bony head shield and jaw apparatus that formed the front section of the animal because the rest of the body was cartilaginous and rarely preserved. The head shield that survives in fossil form is itself extraordinary. Thick, articulated bone plates forming an armored cap over the skull and the front of the body that looks more like medieval plate armor than anything in the living fish fauna. The jaw mechanism of Dunkleosteus is what makes its skeletal remains particularly striking. Dunkleosteus did not have teeth in the conventional sense. Instead, the jaw bones themselves were shaped into self-sharpening blades that functioned as cutting edges, with the geometry of the articulated bone plates producing a jaw that, in biomechanical reconstructions, was capable of generating a bite force estimated to rank among the most powerful ever produced by any vertebrate. The jaw opened through a four-bar linkage mechanism that involved simultaneous dropping of the lower jaw and lifting of the head shield, creating a rapid gape that would have created powerful suction to draw prey into the bite zone before the blades made contact. The skull of Dunkleosteus, when examined in fossil form, is a piece of biological engineering so different from any living fish skull that understanding what you are looking at requires orientation. The articulated plates, the blade jaw, the overall architecture of a head designed around the requirements of armored ambush predation, it documents a solution to the problem of being a large predator in the Devonian Ocean that evolution has not reproduced since the placoderms went extinct, and that looks in skeletal form like it belongs to an animal from a different planet's evolutionary history rather than from this one's past. Spinosaurus aegyptiacus presents a skeletal reconstruction story that has been revised dramatically in recent years, and that, in its current most supported form, produces an animal whose overall skeletal proportions are so strange that they were initially dismissed as implausible when first proposed. Spinosaurus was the largest known carnivorous dinosaur, longer than Tyrannosaurus rex at estimates of 14 to 18 meters or more, and it is known from partial remains that have been discovered, rediscovered, and reassessed across more than a century of research. The most dramatic feature of Spinosaurus is the elongated neural spines along its back, which would have supported either a tall sail or a more muscular hump structure depending on which interpretation is current, and which in either case produced a dorsal profile unlike any other large dinosaur known. What recent discoveries and biomechanical analysis have added to this picture is even stranger. Spinosaurus appears to have been primarily aquatic, more adapted to moving through and hunting in water than any other large theropod dinosaur known. Its nostrils were positioned high on the skull rather than at the tip of the long, narrow crocodilian-like jaws, keeping them above water while the jaws were submerged. Its center of mass was positioned differently from other large theropods, with shorter hind limbs and denser bone than bipedal terrestrial theropods. Bone density more consistent with an aquatic animal managing buoyancy than with a fast terrestrial runner. Its feet appear to have been paddle-like, potentially webbed, suggesting propulsion through water. The skeletal reconstruction of Spinosaurus that current evidence supports, a massive, sail-backed, semi-aquatic predator with a narrow crocodilian skull, short dense limbs, and webbed feet hunting fish in the river systems of Cretaceous North Africa, is so different from any other large predatory dinosaur known that it looks in illustration form like the product of several different animals' evolutionary pressures being applied simultaneously to one body plan. The skeleton, in its current most evidence-supported reconstruction, is strange in exactly the way that the fossil record is strange, when it shows you a solution that the living world has no equivalent for. The skeleton of the star-nosed mole, Condylura cristata, belongs in this discussion because it represents skeletal strangeness at the opposite end of the size scale from Patagodontan and Spinosaurus, but with its own specific architectural extremity that is worth examining. The star-nosed mole is a small North American mole whose defining feature is immediately apparent from the skull. The nasal region supports 22 fleshy, mobile appendages arranged in a star pattern that together form one of the most sensitive touch organs in any mammal. The skull of a star-nosed mole shows the nasal bones and surrounding structures shaped around the requirements of supporting and moving this elaborate sensory apparatus, and the neurological representation of the star in the mole's brain is disproportionately large. The amount of brain tissue dedicated to processing sensory information from the star exceeds the total brain tissue dedicated to all other sensory systems combined. The skeletal and neurological package of the star-nosed mole is the product of evolutionary refinement for an environment, underground tunnels and underwater foraging in the dark, where touch sensitivity at extremely close range is more valuable than any other sensory modality. The result is an animal whose skull, combined with the soft tissue and neurological structures it supports, is a piece of sensory engineering so refined and so different from what a standard mammalian skull accomplishes that it belongs in any account of the extreme ends of biological skeletal design. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. Hallucigenia sparsa needs to be in this accounting despite being a soft-bodied organism whose skeletal remains are minimal, because its discovery and the subsequent century of debate about which end was which and which side was, the top represents one of the great stories of paleontological confusion and eventual resolution that the Cambrian fossil beds of the Burgess Shale have produced. Hallucigenia was a small, worm-like Cambrian animal approximately 508 million years old, preserved in remarkable detail in the Burgess Shale deposits of British Columbia. And its preserved structure was so unlike anything living or previously known that its original description placed it upside down and backward simultaneously. The spines along what turned out to be its dorsal surface were initially interpreted as legs. The tentacle-like structures along what turned out to be its ventral surface were initially interpreted as a dorsal fringe of some kind. The debate about basic body orientation persisted for decades because the animal was so structurally unlike anything in the modern or then-known fossil fauna that standard biological frameworks provided no reliable guide for interpretation. When the claws at the ends of the appendages were eventually identified and the body orientation was finally established, the animal that emerged from the revised reconstruction, walking on paired tentacle legs tipped with claws, bearing a dorsal row of protective spines, with a distinct head end bearing eyes and a circular jaw, was strange enough that the name, which had been given before the body orientation was understood, remained appropriate. The Cambrian is full of animals whose skeletal and body plan remains produce this quality of disorientation. The period represents an explosion of body plan experimentation in which evolution was apparently trying combinations of structures that have no living descendants and no equivalent in the subsequent fossil record. Anomalocaris, the large Cambrian predator with grasping appendages at the front of its head and a circular jaw made of overlapping plates, looks in skeletal reconstruction like an animal assembled from incompatible parts. Opabinia, with 5 eyes and a grasping proboscis extending from its front end, produced laughter from the scientific audience when it was first presented at a major conference. Not because it was funny, but because the reaction to seeing something that's strange and real simultaneously can apparently produce laughter rather than any other available response. The skull of the narwhal, Monodon monotros, is strange in the specific way that extremely familiar things become strange when you look at them carefully for the first time. The narwhal's tusk, the iconic spiral protrusion that can reach 3 meters in length and that has been associated with unicorn mythology across multiple cultures, is a tooth. Specifically, it is the left upper canine tooth, which grows in a continuous spiral through the upper lip and forward from the skull in a left-handed spiral pattern. The right upper canine typically remains embedded in the skull as a small vestigial tooth that does not erupt. In rare cases, both canines erupt and spiral forward, producing a 2-tusked narwhal that looks even more improbable than the standard configuration. The narwhal skull, examined in skeletal form, shows a face from which a single, enormous spiraling tooth emerges through the lip, a structure so anatomically unexpected that the first European naturalists to describe it from specimens did not accept that it was a tooth. The function of the narwhal tusk has been debated across centuries, with hypotheses ranging from ice breaking to echolocation enhancement, to sexual selection signal to sensory organ. Recent evidence suggests the tusk surface is densely innervated in ways consistent with sensory function, potentially detecting temperature, pressure, or chemical gradients in seawater. An animated tooth, 3 meters long, spiraling out of an Arctic whale's face, and potentially functioning as an environmental sensor, the skull that contains this structure is one of the stranger objects that the mammalian body plan has produced. The internal skeleton of the mantis shrimp, Stomatopoda, deserves mention because the mantis shrimp is often discussed in the context of its extraordinary vision, 16 types of photoreceptors compared to the human 3, but its skeletal and physical structure includes a strike mechanism whose engineering is remarkable in purely structural terms. The dactyl clubs of mantis shrimp, the hammer-like appendages used to strike prey, capable of accelerating to approximately 80 kilometers per hour in less than 3 milliseconds, and delivering impacts that generate cavitation bubbles that inflict additional damage when they collapse, are structured with a herringbone pattern in the mineralized club region that distributes impact stress in ways that prevent catastrophic failure. Material scientists studying mantis shrimp club structure have found that the architecture of the impact region is unlike any human-engineered impact-resistant material currently in use and has inspired research into new composite material designs. The biological skeleton is outperforming human engineering in a specific structural challenge, and what it has produced is strange enough in its microscopic architecture that the mantis shrimp belongs in any discussion of skeletal design extremity, even though it operates at a scale that is invisible without a microscope. Megalodon, the extinct shark whose teeth appear in the fossil record in sizes that make modern great white shark teeth look modest, does not preserve its skeleton in the way bony fish and terrestrial vertebrates do because sharks are cartilaginous and cartilage rarely fossilizes. What the fossil record of Megalodon contains is primarily teeth, enormous, serrated, triangular teeth that reach lengths of 18 centimeters or more in large specimens, and vertebral centra, the calcified sections of shark vertebrae that do sometimes preserve. From these elements, size estimates for the full animal range from 15 to 20 meters, though the upper end of these estimates is debated. The teeth of Megalodon, arranged in the reconstructed jaw structures that museum displays use to convey scale, produce the same quality of cognitive vertigo as the patagotitan femur, the encounter with a size of animal that the living ocean does not prepare you for. A Megalodon tooth in hand, examined next to a great white tooth, communicates something about the scale of the animal it came from that photographs only partially convey. The preserved element is strange because of the extrapolation it requires, from a 17-centimeter tooth to the skull that contained it, from the skull to the body behind it, from the body to the ocean it moved through. The axolotl, Ambystoma mexicanum, presents skeletal strangeness of a different category, not extreme size or bizarre protrusions, but the specific strangeness of an animal that retained the skeletal characteristics of a juvenile throughout its adult life through a phenomenon called neoteny. The axolotl, a Mexican salamander, never completes metamorphosis under normal conditions. It retains its larval features, including external gills, throughout its adult life, reaching sexual maturity and reproducing while still in what would be, in related species, a juvenile body form. The skeleton of an adult axolotl is partially cartilaginous in regions that would ossify during metamorphosis in other salamanders, maintaining a juvenile skeletal architecture in a sexually mature animal. The axolotl skeleton is strange in the way that a developmental program running differently from its expected trajectory is strange. It reveals that the endpoint of skeletal development is not biologically fixed, but is a target that can be moved or removed by changes in the hormonal and developmental signals that control metamorphosis. The axolotl stayed larval, reproduced, and became a distinct species organized around the larval body form. Its skeleton is the record of that developmental divergence. The full range of skeletal strangeness that the fossil record and living animal diversity contains is a document of every extreme that biological engineering has reached in the approximately 540 million years since the Cambrian explosion produced the first hard-shelled animals. From the 70-ton Patagotitan to the heavily innervated narwhal tusk, From the self-sharpening blade jaws of Dunkleosteus to the herringbone, impact-resistant strike club of the mantis shrimp, the skeleton record is not just a catalog of what has existed. It is a catalog of what a body can be, of the full range of structural solutions that evolution has produced for the problem of being alive in the specific environments and ecological contexts that have existed on this planet across deep time. The strangeness is not accidental and it is not random. Every strange skeleton in this tour is strange for a reason that, when you understand it, makes the strangeness feel like inevitability. The specific, pressured, tested inevitability of a solution that natural selection refined because it worked better than the alternatives available to it. The Babirusa's upward curving tusks, the Spinosaurus's paddle feet, the narwhal's spiraling tooth. Each is the endpoint of a selection process running in a specific ecological context with specific available starting materials for long enough to produce something that looks, to eyes calibrated by the living world, like it should not exist. The fossil record is full of things that should not exist. That is precisely what makes it worth looking at.